This is Garis MPC, Mathematics, Physics, Computing. It's 130 plus Masters and PhD level courses on pure math and mathematical physics. This is course number 4, MPC 4, on linear algebra. This is lecture 2 on the theme of linear equations, and this is session I. We're in the process of going through various kinds of examples of actual solutions to the system of linear equations. With the first concrete example covered the case of inconsistency, so there's no solution. Second case covered where the number of equations was equal to the number of variables, in which case theorem 2.2, an earlier session, says that the solution is unique, and previous session we did an example of that where we got a unique solution. So I guess from the theory, this example should be the case where the number of equations is less than the number of variables, in which case we should get more than one solution. Surprise, surprise. All right. Let's see. So example 2.6, we're given, here's your system. Remember, just a set of linear equations. So let's put one equation per line, one equation, one line, one equation. So here's equation 1 on line 1, equation 2 on line 2, and so on. And we have what? 1, 2, 3, 4 variables or unknowns, and 3 equations. All right, so through Gaussian elimination, let's see, our first equation, the coefficient here is 1, so not 0, so that's okay. So we don't need to swap around 2 equations such that the top equation has a non-zero coefficient here. This is okay as it is, so just leave it. Right, so we now want to eliminate the x term in the second and third equations. So how to do that? So line 2 needs to be replaced by what? Well, line 2 minus twice line 1, I guess. Let's have a look. So line 2 becomes line 2 minus 2 times line 1. Okay, so that will get rid of the x. So line 1 stays the same. So line 2, this will be replaced by this, which works out to be this. And let's see, how can we get rid of the x term in line 3? By replacing line 3 by what? By line 3 minus 5 times line 1. That'll get rid of the x term. So line 3 should be line, what? Hold on, let me check. Line 3 should be, that should be a 3, I think. That should be a 3. Okay, so that will get rid of the x term, and work it out, and you'll get this. Right, now what to do? Now we forget about the upper line. We now have this smaller or subsystem of 2 equations in 2 unknowns. So how So we'll keep this one and try to reduce this one. So we want to replace this line, we want to replace L3 dashed by an equation where the z term is missing. We want to Gaussian eliminate the z term. So how to do that? So line 3, replace it by what? Line 3 minus 2 times line 2. So line 3 becomes line 3 minus 2 times line 2. Alright. So that stays the same. Here it is here. Of course that stays the same from before. And this gets replaced by whatever this comes out to be. And it comes out to be 0 equals 0. Now remember earlier session, when you get an equation of that form, 0 equals 0, it's useless. Doesn't tell you anything about the variables, the values of the variables. So just throw it out. So we end up with this. So we have here now we have a system of 4 with 4 variables and 2 equations. So that from theorem 2.2, that says there's usually more than one solution. So let's, now is it consistent? The system is consistent if each equation is consistent, and an equation is consistent if it is not inconsistent, and an equation is inconsistent if it's of the form 0 equals b, where b is non-zero. Now this is not 0, right? So each equation is consistent, therefore the system is consistent. So the system is consistent because there is no because there is no equation of the form 0 equals b, where b is non-zero. Now the number of equations are in the echelon form is 2, right? And 2 is less than the number of variables, which is 4. So so there are more unknowns than the number of equations, and it's in echelon form. So that may imply an infinite number of solutions. Okay, now to say, I mentioned this a little bit earlier, talking about the concept of the free variable. Now I gave a definition of what a free variable is. A variable is free if you can give it any value you like. It's free in that sense. So now we're going to talk about for this system which are its free variables, and I'll need to define what that means. And to be able to do that, I need to introduce another concept, and that's called the pivot. In ordinary English, I think pivot is the point about which something rotates. Okay. Now there's not really rotation, so I'm not quite sure why that point was chosen. Anyway, so I need to explain what a pivot variable is. At pivot, that's P-I-V-O-T. And I can explain what the free variables are in terms of the pivot variables. So what's a pivot variable? You have a look at each equation, and the pivot variable is the leftmost one. So in this case it would be x, and the second equation z. So we have 2 pivot variables amongst the 4 variables in this system. So, and they are x and z. And by definition, the free variables are the others, just the other variables, the non-pivot variables. So obviously the 2 free variables will be y and w. Okay. Now, by the way, I was quite unhappy actually with Lipschutz handling of the notion of the free variable. I didn't find it clear at all. So eventually I had to go to the internet and look at other people's definitions of what a free variable was, until I came across one in what I just gave you, which is very simple. Once you understand what a pivot variable is, then the free variable is easily defined in terms of the pivot variable, as I've just done. Okay, so just summarizing quickly, a pivot variable is the variable that's to the leftmost variable in your equation. So x here is the leftmost, so that's a pivot variable, and z is also a pivot variable here because it's the leftmost one in this second equation. So that your two pivot variables are x and z, and by definition the remaining variables are called your free variables. So they'll be y and w, and that means you can give your free variables any value you like. So once you give a value to y and to w, that will then, because of the two equations and these two fixed values that you've now given, they will then, those three things, four things, so the two equations and the two values for y and w, the free variables, those four things will specify the values of x and z, as you will see in a moment. Alright, so we've defined pivot variable, free variable. So let's now, with the free variable, you're free to give it any value you like. So let's try to find a particular solution to this system, this set of equations. So let's just randomly choose variables for the free variables. So for example, y equals -2 and w equals 1. All right? Well, once we know w is 1, so we know z minus 2 equals 1. So z equals 3, is that right? So z equals 3. So we know that's 3. We said w was 1. What did we say? So z is 3. So y we know, so we can calculate what x is.